Okay,
Thank you for
thank you so
joining
much
us.
for your kind introduction. So the title is on the slide. So the simulation of high-speed compressible flows with shock waves in the presence of dense layers of particles, that is, layers with a significant volume fraction of particles, are relevant in various fields. These simulations arise, for example, in the explosion safety issues, for example, dispersion of particles behind a shock wave during, dust explosions, or explosion safety coatings. They're also relevant for the development of promising fire extinguishing systems where shock-induced gas particle jets play a significant role, or aerospace research, interaction of exhaust plumes with the surfaces of extraterrestrial bodies during spacecraft landings, and many other applications. I have shown you just a few examples to prove the relevance of the topic of my speech. As for modeling issues, there are two frequently used approaches depending on the choice of the two length scales, microscopic or macroscopic. At the microscopic scale, the particle phase is treated as discrete particles, and each particles is tracked individually. So this is the Eulerian-Lagrangian approach, right? At the microscopic scale, the particle phase is modeled as a continuum media. And in this case, equations for a continuous media are solved. This is Eulerian approach. Eulerian-Lagrangian models such as CFD discrete element method can provide information regarding each particle trajectory, position, velocity, and so on. And they have been widely used for the simulations of interactions of shock with particles. However, such simulations are highly computationally expensive. Although you can see that, for example, here and here, the Eulerian-Lagrangian approaches were used. On the other hand, Eulerian approach becomes a more practical alternative to simulate real-world granular systems, where a large number of particles are taken into account and where the scale of the problem is greater than the scale of each particle. For highly packed granular bed, where particle collisions are dominant, Barnum-Zeta-like models are used, as well as models based on the kinetic theory of granular media, or some other models, for example, models of academician Igmatulin from Russia. So my talk will be about the usage of Barnum-Zeta-like models for the simulations of problems about interaction of a shock wave with dense layers or beds of particles. First of all, I'd like to remind the audience or explain what is the Barnum-Zeta equations, because the models based on these equations are used in my work. So initially, this model was formulated for the problems of deflagration to detonation transition in heterogeneous explosives. In this paper, actually, from historical point of view, from historical perspective, there are also earlier works with almost the same results, but everybody knows this work. The model comprises mass, momentum, and energy equations for the solid phase, mass, momentum, and energy equations for the gaseous phase. So we have density, pressure, and velocity for each phase, and also volume fraction. So we have 7 unknowns. And we should add one more equation. And in this paper, the so-called compaction equation was added. But it was added in a special way. So this equation and also terms C, M, and E that are responsible for the interface interaction, they were added in such a manner that the entropy inequality for the mixture would be valid. So in this sense, this model is thermodynamically compatible. And so this is a very good property of this model. Important feature of this model is that both phases are compressible. So gaseous phase is compressible and solid phase is compressible. So solid is a sort of weakly or truly compressible medium depending on the application. So another good property of this model that it's hyperbolic for a wide range of parameters. It means that we know, generally speaking, the correct statement, all these things about characteristics, and we can try to adopt known methods for the hyperbolic equations and so on. On the other hand, the system is difficult for the numerical solution because of these non-conservative terms that should be treated carefully, because they significantly affect to the solution, especially for the cases when we have explicit interface boundaries. This is the sketch of the model. So this is Eulerian volume of the two-phase medium. We have particles or propellant, if we are talking about combustion, and air, and each phase has its own set of parameters, and there is an interface interaction, and also there is explicit interface boundary, and we should define some parameters at this boundary. And once again, they were also chosen to entropy inequality to be valid. So this is the general framework of the mathematical model. It is mentioned that very good properties of this model is the reason why this model is widely used now for many other applications, not only DDD in heterogeneous explosives. So it's used for high-speed interactions of solid and fuels, and for example, two-phase flows in pipes, study of physics of single droplets or bubbles, because this model can be used when we have truly two-phase media, and also when we have explicit boundaries. So this model can be used for droplet resolve to particle resolve simulations. There are many other subsequent developments of this model, simplifications, and so on. At the same time, you can see that in a number of applications, this model is used when the solid phase is very weakly compressible. So even in case when, in fact, the solid phase is almost incompressible, we can relax this restriction and consider it as weakly compressible to have good properties of the model. Apparently, for the first time, the simulations of shock wave interactions with dense layers of particles were carried out in works of Professor Sorrell. Now, this team from Japan also carry out such simulations. I'd like to show you some background. So I have some experience in such simulations. The problem is that there are few experimental works that can be used to validate, to analyze the models for such flows, because it's very difficult to look inside the dense layer of or curtain of particles. For example, in this paper, Rockwith authors, they considered interaction of a shock wave with a dense curtain of particles. So the shock wave interacts with this curtain, and they had 3 pressure transducers, one located upstream and 2 downstream, and they measured the reflected wave and transmitted wave. And here the curtain was movable, and so it moved. And the difficulty from numerical point of view is that we should correctly describe this motion of cloud, and so this blue transducer demonstrate the motion, the moment of arrival of particles. And so we should be able to describe it correctly. So another test case is interaction of shock wave with a layer of particles on the surface. So it is known from papers started from late 70s that under some conditions, the pressure transducer located under the layer on the surface can show the pressure increase. So if the dispersed phase is involved into the motion, then we can get the pressure rise under the layer of particles. And so we compared our simulation results with the experiments of Gelfand with co-authors from Simonov Institute of Chemical Physics. So the green curve is gaseous pressure due to filtering process, and the red curve is solid phase pressure, and blue one is some averaged pressure, and we compare it with experimental data, both qualitatively and quantitatively. And so our recent work is about interaction of a shock wave with the layer of particle. So this is another actually famous in this field paper of Fan with authors. They measured the granular contact angle and transmitted compaction wave angle. So they try to define quantitative parameters that define the process of lowering of the boundary of this layer under the action of a shock wave. And in our simulations, we were able to explain the dependency of these angles on the intensity of the shock wave. So for the stronger shock wave, we have particle plug in the layer with higher volume fraction that prevents gas from for the motion inside the layer. So this is a non-obvious dependency of these angles on the intensity of the shock wave. So I have shown you this background to demonstrate some experience in such simulations, and now I'd like to show the results on the current problem. These are the results, recent results actually, of experimenters from UFA Petroleum University. These guys, they're interested in study of water gas saturated bulk media. So, for example, if you have sand with some volume amount of water, and they considered experiments in shock wave, so in shock tube. So they have a conventional shock tube, and this is a section of granular media, comparatively long, and this setting, this statement of experiments differ from many other because they generated shock wave, and they considered not a single action, not a single impact of this shock wave on the particle bed, but they considered also a reflection of the shock wave from the surface of this bed. Then shock wave propagated, reflected from the upper wall of the shock tube, propagates down, and so on and so forth. And they had several impacts that impacted the granular media. So these are the experimental data. You can see the red line depicts, so correspond to the pressure signal here on the pressure transducer D1 outside the bed. So just several pressure pulses that propagates back and forth. What they got in the particle bed, they had D2, D3, and D4, so 3 pressure transducers. For example, D2 is the green line, and they got just these smeared signals corresponding to the filtering process. But at the same time, after the second impact of the shock wave, they got sharp peaks on D2 and D3 pressure transducers. So they have some unknown, some difficult for their process inside this bed, and so they were wondering in some explanation of this effect. At the same time, we can see these peaks on D3, but if you look at the pressure curve on D4 transducer, we can see just typical curve for the pressure that was attenuated by granular media. So this is also a little bit unusual because, for example, in this case, we see the amplification of pressure under the layer. But here we can see amplification somewhere inside the particle bed, not under the layer. So the goal of this work is simulation of this experimental data. This slide shows how the general Byron-Zeta-like model was adjusted for this problem. So a very important thing here is that we should take into account the real rheology of, not real, but some realistic rheology of particles bed. That is why we should introduce effect of intergranular stresses inside particles. So there is a potential energy of compaction or granular energy inside the total energy of solid phase. We follow the initial paper of Byron and Zeta, and also subsequent papers of Zila and Capilla, where they modified and changed a little bit the terms responsible for the works of compaction forces. And actually, we used the notations from Schwendemann paper. So parameters with the bar correspond to particles, parameters without a bar to the gaseous phase. So this is, again, the sketch. So we have the particles, and what does it mean, intergranular stresses? So it means that particles could not be compressed more than closing packing limit. And this effect should be taken into account. So when volume fraction of particles become significant, too big, we get higher pressure inside the particles that prevent from following compression of particles. These are the equations for submodels. Very important thing is how can we choose this function for potential energy of compaction. In many papers, the following function is used. So it's 0 if volume fraction of particles is lower than some critical value, and it's some algebraic function that should be calibrated according to the experimental data if volume fraction of particles is higher than some critical value. In literature, you can find also a continuous function to describe this potential energy of compaction. But in this work, we use this one from Sorrell paper, and it mimics the, real physics of particles under compression. Although, as I said, many other choices for this function are possible, and for sure, all this affects the results of simulations. We use just common standard formulas for interface friction between gas and particles. As for numerical scheme, so as I said, that numerical solution of Baranzata-like system of equations is not a simple question. The difficulties occur at the level of the mathematical formulation of the model, because in contrast to the just, for example, Euler equations, we cannot define the weak solution of the system of equation in the same manner because of non-conservative products. And for example, the Riemann problem solution for the Baranzata equation is not unique. And strictly speaking, we should add some more assumptions to define one weak solution. Very often people do not pay attention to that, and they just use some numerical method, and the choice of weak solution is carried out explicitly on the level of numerical method. However, I prefer to use this Godunov method from Schwendemann paper, because at least we understand which assumptions were used to formulate to find the unique solution of the Riemann problem for the Baranzata equations. So the general framework for the numerical method is the strength splitting approach. So first of all, we use hyperbolic operator. So it's very common for the solution of such sort of equations. Then a relaxation process. So from physical point of view, we should relax pressures after hyperbolic step, and then algebraic source terms. For the hyperbolic step, we use Godunov method. The key part is the solution of the Riemann problem, and the solution of Riemann problem also provides automatically provides the approximation of the non-conservative terms. So this is very convenient, although this U star is a little bit difficult to construct. So we also have many cases depending on the gap between volume fractions of particles to the left and to the right of this continuity. So all the details, for example, are described here in our paper in multi-phase flows. How to combine different cases for the solution of the Riemann problem to the Baranzata equation to one numerical flux. Pressure relaxation term is also very important, because here we take into account the intergranular stresses. So we use stiff pressure relaxation here, although it's not necessary, and maybe it's also important and effective result, and we should study the pressure relaxation with some finite value of compaction viscosity. So after pressure relaxation term step, we find the correct parameters inside computational cell to be this condition be valid. So pressure in particles should be equal to pressure in gas plus intergranular stresses. So this is the relaxation term. And finally, we take into account interface friction force. So this is the, in a common words, the numerical algorithm, but each phase, each step for sure can be described in more detail if it is necessary. So the results, simulation results. So now I'd like to explain how can we reproduce the experimental data and give some explanation of this. Actually, this experimental effect, I can say it can be called a new one, because I don't know, I'm not aware of works in which this amplification of shockwave occurred inside this bed. Usually people consider the process on the surface under the layer, not inside the bed. For sure, there are a number of papers of Britton, of Gabi Bendor with co-authors, but I didn't see such effect in their papers. So this is the whole length of the shock tube. So this is the first pulse generated by high pressure chamber. So this is a shock wave and compression phase and refraction wave. It propagates. This is the location of D1 transducer. And we can see this first pulse. We can see some discrepancy, some error in comparison between simulation results and experimental data. Actually, I'm in contact with experimenters, and I took the data from them initial. Maybe the problem here is that the diaphragm was not ruptured by external means. It was ruptured by itself when the pressure in the high pressure chamber exceeded some limit, and that's why maybe in high pressure chamber the parameters were not uniform, and all this actually affects the process. So that is why there could be some error here, even in the incident pulse that impact the bed. So this is the bed of particles, and we can see the interaction of the shock wave, the formation of transmitted wave. So just filtering wave in gas because it's very dense bed, the reflected wave. And we can see that actually pressure here is higher than in the incident wave because of reflection of the wave from a dense layer of particles. And we can see the increase of volume fraction here. So the beginning of layer compaction. You can see that for the following pulses, in general, the correspondence of the moments of arrival of a signal on D1 is okay. The most interesting thing is the comparison pressure signals inside the bed. So this is D2. D2 is the pressure transducer inside the bed, but close to the surface of the bed. So the blue line corresponds to the gaseous phase, and the orange line corresponds to the pressure in the solid phase. And so we can see that when the volume fraction of particles exceed the alpha critical I have shown you in the model, then the intergranular stresses occurs, and we can see it here in the form of peaks. If we compute this volume fraction average pressure, we can see actually pretty good relationship of computed and experimental data. So looking at D2 transducer, we can say that apparently these peaks are due to propagation of compaction waves inside the particle bed. This is D3 transducer. There are some discrepancies, but generally speaking, the simulation results and experiments, there is some correlation between them. But as for D4 transducer, there are problems. So this is the experimental data. It's just this light blue curve. And if it would be just gaseous pressure in simulation, so the comparison is okay. But these intergranular stresses produce much more higher pressure. So it means that in my simulation, the compaction wave is not attenuated during propagation inside the bed. Actually, it attenuates, but not not so intensive as it should be. So then I explain this in these diagrams. So this is the interaction of shock wave with boundary of particles. It generates this compaction wave. So we have wave and gas, wave and particles, and so the compaction wave propagates. And these are the locations of transducers D2, D3, and D4. And I have chosen the moments when the compaction wave arrives to these transducers D3, D4, and so on. And this spike occurs when the compaction wave reflects from the wall of the shock tube, then propagates in the opposite direction to the surface of the layer, and then the second pulse from gas comes. And the interference of second pulse from gas and compaction wave from the first pulse that reflected from the bottom wall of the shock tube, they provide those sharp peak on pressure transducer. So this is one of possible explanations of this peak formation. So I have no more time to describe it in more detail. However, it's possible to get in principle this effect of formation of pressure peaks inside the dense layer of particles, even in a quantitative manner with the comparison with the experiments. But at the same time, there are many points to work on. We can take into account the finite value of compaction viscosity, different functions for compaction potential. So maybe this can, improve the comparison of experimental simulated data on D4 pressure transducer. So I finished. Thank you very much for your kind attention.
Thank you very much.